And now, to get the final reflection coefficient, we need to compute the exact value of the semi-classical integral p dx. Because before, we computed its asymptotic value for large values of x. But here, what we do is just what we need to do. We need to extract the imaginary part of this integral. Indeed, there is an imaginary part because x naught plus point is positioned in either turning point, and it's positioned in a complex plane. So what we do is split the integral in a standard way from x naught plus to 0 and from 0 to x. And the second integral is real. And it just adds some arbitrary phase to our scattered or transmitted or reflected wave. This integral, however, contains an imaginary part which contributes to the reflection coefficient itself. So let us compute it. We denote it by minus phi naught. And here we go. So this integral is simply, so this p is e plus u naught over so it happens that the integral can be computed exactly. You just introduce the change of variables. Let me look it up. OK, just a second. Yep. So u, new variable, is just cosh squared of x over a. And let me draw the contour in a complex plane. So here is our pole x1. And here is the turning point x naught plus. And initially, the integral goes from 0 to the turning point. After this change, the integral is turned to the integral in the complex plane of u variable. And it actually stretches from, well, you can look it up. So when x equals 0, then u equals 1. So it goes from 1 to the turning point. But the turning point corresponds to, OK, it's when this square root becomes 0. So u actually equals to minus u naught over e. So let's call it minus lambda squared. So this is the new contour. And after the change, you get the following expression. From 1 to minus lambda squared. OK. And in just square root of u plus lambda squared divided by 1 minus u, and du over u. So the contour seems to have a pole du over root at point u equals to 0. That's due to the fact that when we go from 0 to x naught plus, we actually go in the vicinity of this pole of the potential. And this u corresponds precisely to the, well, it lies close to the pole of the potential. So if you analyze carefully, you should circumvent this pole above in the complex plane. Right. So, and finally, this is more or less standard type integral. Actually, it can be already computed with the help of just contour integration and Cauchy theorem. But you can make another change which even more simplifies it. Namely, the change is as follows. So we just standard fractional rational change of variables. Right, so after this change, and sorry, of course, there is a prefactor here. The prefactor is minus so after the additional change, you get even more suitable expression from 0 to plus infinity, square root of v dv divided by 1 plus v and v minus lambda squared. And the contour itself is similar to the previous one. Again, we have our pole at point v equals lambda squared, and it should be circumvented above the pole. Right, and this integral can be computed with elementary methods. And what you get in the end is pi I a k naught over 2 1 over 1 plus I lambda. As you remember, lambda is much smaller than 1 because we consider the shallow potential well. And so this factor is dominant. So after this, you recall the expression for the wave function. And the wave function is, remember, contained two exponential e to I pi dx plus 2I sine of pi mu times e to minus I pi dx. So now we extracted the imaginary part from both of these integrals. So now they look as follows. So now it's the real part from 0 to x minus the phase pi naught. And here the same thing. So of course, the crucial role belongs to the imaginary part of this phase. So and the contribution is just plus imaginary part of phi naught, and here it's just minus imaginary part of phi naught. So as a result, the reflection coefficient, well, of course, the amplitude is doubled, right? So the amplitude of the reflected wave comparing to the incident wave is doubled. So, and the reflection coefficient is the square of the amplitude. So what we get is 4 sine squared pi mu times into minus 4 imaginary part of this phase phi naught. And we plug in this expression and finally get the resultant reflection coefficient minus 2 pi a k naught. And sorry, I forgot to mention that k naught, which repeated earlier, is just our standard wave vector of the incident wave. So here's the answer. It coincides with the answer with the exact answer for the same problem in the limit k naught a is much greater than 1, so in the semi-classical approximation. And it contains all the specific features, namely it contains this prefactor, which reflects the reflectionless property of our potential. And with the help of this scheme, or this turning point in the complex plane, we managed to recover this beautiful pre-exponential factor.